All right, and we're live. Okay, so this week we're basically addressing this question here. This isn't a framing question, although the first framing question is similar to it. This is like a title for the whole set of slides. How do we make solutions? And really that's the heart of what a lot of what we do in chemistry is making solutions. And so we need to start talking about how do we do this? How do we do this? How do we do this? Yeah. All right, so our first framing question, very much like it. How do we make simple solutions? How do we make simple solutions? How do we make simple solutions? One thing you'll find is chemistry is a fairly common activity to participate in. And you find this when we talk about what a simple solution actually is. So in order to address this question, we need to talk a little bit about water. So water is known as the universal solvent. Water is known as the universal solvent. And what that means is basically this next point here. You could look at it as this is why water is the universal solvent, or this is what it means for water to be the universal solvent. That water is polar, like the Earth is polar, right? North Pole, South Pole. Water has that kind of property as well. Water is polar. It has different regions within the molecule. And so because water is polar, it dissolves anything that is either polar or charged. Okay? So water dissolves anything that is either polar or charged. And you're like, wow, that's awesome. This is the most exciting thing that I've heard, not just all day, but really all month. I completely understand, but you don't maybe not fully understand what this actually means. Now, I will tell you the overwhelming majority of molecules on Earth would fall into this category, that they would be dissolved in water. And this is why water is known as the universal solvent, because almost every chemical reaction that takes place in our bodies, or meaningful chemical reaction that takes place anywhere on Earth, is done in water. Have you ever heard that our bodies are 75 to 80% water? Have you heard that before? Have you ever wondered why? The reason why, there are actually two main reasons why, but one of them has to do with the chemistry, because water dissolves almost everything. And so basically every meaningful chemical reaction that takes place in your body has to take place in water. So you need a lot of water to make that happen. You need a lot of water to make that happen, so that everybody can go for a swim, right? Make sense? Okay, so water, universal solvent. Water is polar. It's going to dissolve anything polar or charged. We'll talk more about what those terms mean in a couple of weeks when we start really getting into the nuts and bolts of how chemical reactions take place. Come on in. Another thing you need to know about water is that water has a density of 1 gram per milliliter. 1 gram per milliliter. We've talked about density quite a bit already. Density is the amount of mass in an object divided by the amount of space that object requires. What's the significance of this being 1 gram per milliliter? When you think of what that actually means, what that enables us to do, if it's 1 gram per milliliter, how many grams are in 100 milliliters of water? 100 grams, right? How do we know that? Because there's 1 gram for every 1 milliliter. How many grams are in 300 milliliters of water? 300. How many grams are in 87.5 milliliters of water? 87.5 grams. This is so wonderful because what it allows us to do is to immediately change the volume of water into the mass of water. And this is really nice. You don't yet appreciate why that's nice and significant, but you will shortly. Okay? That you can immediately change from the volume of water into the mass of water. Now, can you think of some exceptions to this? Last week we talked about that there are some other units. What if it's not in milliliters? Right? What if you want to know what is the mass of 3 liters of water? What would you do? How would you do it? Luckily for you, we can convert from liters to milliliters, right? In the same way you could figure out how many cups are in a gallon, right? Which, by the way, there are 16 cups in a gallon. I don't know if you knew that or not. Fairly arbitrary. But in a liter, there are 1,000 milliliters. Remember that? Because milli, that prefix we talked about last week, means 1/1000th. So if there are 1,000 milliliters in a liter, how many milliliters are in 3 liters? Whoa, that is... Oh, that was in. Did you see that? That was goaltending. 1 equals... Nobody in here told me that you are... Oh my gosh, thank you so much. That was so kind of you. 1 equals 1,000. So 3 equals how many? 3,000. How do we know that? How'd you do that? You did algebra, right? But you just did it in your head. You didn't even know it. So if 1 equals 1,000, if 1 liter is 1,000 milliliters, 3 liters is 3,000 milliliters. And you did this because you know the conversion factor. So how many grams is 3 liters of water? 3 liters is 3,000 milliliters. And how many grams are in 3,000 milliliters? 3,000. It's 1 to 1, right? And so now you have a wonderful tool at your disposal. And so now all we've talked about is water. We haven't answered this question yet, right? How do we make a simple solution? And the answer is we dissolve something in water. So we could dissolve a salt, which you'll find out in a little bit means that you've got 2 charged things stuck together. You ever heard the saying opposites attract? It's true. And not only do opposites attract, but they form salt when they do. So you can add something to that saying. If ever you hear somebody say opposites attract, say, you know what, you're right. And they form a salt when they do. I'm sure they'll appreciate that. So we can dissolve a salt or anything polar into water, and now we have made a simple solution. Have any of you ever had a recipe that called for making a simple syrup? A simple syrup is sugar in water. It's a simple solution. And sugar, if it dissolves in water, what does that tell you about sugar? It's polar. Look at that. That's critical thinking right there. Applying something you just learned to a new application. I love it. It's well done. Okay? So we can make a simple solution this way, and we can do it this way. We can do it by making what we call a percent solution. We can make it by doing making what's called a percent solution. All right. Let's say we wanted to make a 35% salt solution. This right here is table salt. We'll come back to this in a couple of weeks. But let's say we wanted to make a 35% salt solution. Now notice, it is not telling us what that salt is dissolved in. So it's assumed it's dissolved in water. Why? If it doesn't tell us what we're dissolving this salt in, why are we going to assume it's water? What is water? It's a universal solvent. And so already from here you should have an idea of what this word means, but don't worry because it's going to be one of your key terms. You're going to look it up and then you're going to have a really good idea of what that word means. But let's say we want to make a 35% salt solution. And it didn't give us any other piece of information. It didn't give us any other piece of information. And we were on, okay, well, how could we possibly do this? How could we possibly do this? Notice the percent solution is basically the calculation for doing percent anything, right? If you wanted to figure out what percent of the total biomass you are of your family, right? Have you ever wondered that? Like, what percent of the total biomass of my family do I make up? You would do your mass divided by the total mass of your family, right? Right? That makes sense? None of you have ever wondered about that? I make up exactly 47% of the biomass of my family, which is impressive because there are 6 people in my family, and I am almost half of it. Right? My children are little, they're tiny, so I've got some time. My children collectively weigh like 125 pounds. So, anyways, sorry. That's another story for another time. I have also a really good story for you, which I'll tell you. It's not a good story, it's actually a horrific story, but I want to tell you. But anyways, so we're going to make a 35% salt solution. The easiest way we can do this, if that's all we're given, is let's make this on the bottom equal 100. Right? Because if that's all we're given, it's like the same thing if you do any kind of math where you can make something 1, make it 1, right? Because then that makes it really nice and easy to do. So let's figure out a way to make this bottom 100. Okay? So we're going to do mass of salt plus mass of water equals 100 grams. Okay? All right? We okay with that? Because we want this bottom to be 100. We're going to make it as simple as possible. If 35% of it is salt, 100 grams times 35%. Another way we can do that is 0.35, right? We agree that that's the same as 35%. Is equal to what?
35 grams.
35 grams of salt, right? And then how are we going to figure out how much water we have? Do a little bit of algebra. We could do that. Or, if we know that the salt and the water together have to be 100 grams, we could just take 35 away from 100 and figure out what's left. Right? That makes sense? Man, I realized something. I just said 125 pounds. And then I've been working it in my head, and you know what? It's actually 126 pounds. But that was pretty close. I just said that, and then I added up, we weighed them all last night after the math, and it's 126 pounds. So I lied to you, I'm sorry. But collectively, my children weigh 126 pounds. Okay, so how much of this is water? 100 grams minus 35 grams is equal to 65 grams. And because we set this up to where the numbers are really nice. We wanted 100 grams total. And if it's 100 grams total, we know 35 grams of it has to be salt because 35% of this solution is salt by mass. So the remaining 65% has to be water. Okay? So now we've made a simple solution, and we've done it based on percent. We made a 35% salt solution. And in case you were wondering how that compares to the ocean, any of you wondering that? Ocean water is 3.5% salt solution. So this is a very, very salty solution. And have any of you ever been playing in the waves and you got absolutely destroyed and you weren't ready for it, and so your mouth was open and you just get the drink of the ocean? It's fun, right? It's delicious. It tastes like when you accidentally make a cake with salt instead of sugar. No? Okay. I said it was an accident. Okay. Any questions here? So how can we make simple solutions? Just answer this by saying this. We dissolve something in water. We dissolve something in water. That's how we make a simple solution. We dissolve something in water. And so we can do it to make a percent solution, or we can do it some other way, which the some other way we'll see it over the next 30 minutes. You're excited, right? You're intrigued. You're like, what's going to happen? You know what? What would be a fun lab to do is to bake a cake, but to put salt instead of sugar. And then we can all eat the cake, but we'd have to eat it outside because you can't eat in the lab. And then just so you can experience what that would be like. A friend of mine made a key lime pie. And key lime pies are pretty, they're pretty, I mean, sour, right? I mean, it's got lime in it, it's got some citrus, and he accidentally put salt instead of sugar. And it was the worst experience of my life. Because I was raised to never complain about what you're given. Somebody gives you food, you thank them, you demonstrate gratitude, and you eat it. And that I did. That I did. I could still taste it, in fact, and this was 19 years ago. Still taste it like it was yesterday. All right, so some key terms. I would like for you to look up solvent, and I would like for you to look up polar. So we've already answered this framing question, and I would like for you to look up solvent and to look up polar. All right. So just so you know, I'm not recording the Wednesday class as well. I'm just sending them the recording of this class. So if you feel like you want to say something nice to the people from Wednesday, you have that opportunity. All right, anyways. Next question. What are some important measurements? So as we start to talk about more sophisticated ways to make solutions, rather than just doing it based on mass, we need to talk about some important measurements. Oh, the first one. This is my favorite. This is my favorite number in the whole world, by the way. A mole. A mole. Actually a number. It's also a small mammal, insectivorous mammal. Several different species of mole, in case you were wondering. But a mole of a material is an actual amount. It's a number equal to Avogadro's number. Wow, this is so good, right? We're making connections to what you already know. Like, I've been talking about Avogadro's number all week. All week. I mean, it's only Monday, so it's only day 2 of the week. That's good. It's a good way to start your week. A mole of material is an amount equal to Avogadro's number. What's our question? What is Avogadro's number? Is it like a dozen? Right? Is it a gross, which is a dozen, right? What is this number exactly? Here it is. 6.022 times 10 to the 23rd power. That is a big number. That is a big number. Now this is maybe a new way of writing numbers for you. So I want to show you what this actually means. This may be a new way of writing numbers for you. So let's say instead of 6.022 times 10 to the 23rd power, let's say it was 6.022 times 10 to the 3rd power. Okay? Yeah?
You move the decimal point over to 3.
You sure do. Because 10 to the 3rd power happens to be 1,000. Because it's 10 times 10 times 10. 10 times 10 is 100. Don't know if you knew that or not, but you're welcome. And 100 times 10 is 1,000. My daughter's 7, and she is very opposed to using the word 1,000. She wants to use 1,000. Because she's like counting, and she'll get to like, I don't know, she'll sit there and on long road trips, she'll just keep counting until we make her stop. And so she'll get to 1,000, but she won't say 1,000, she'll say 1,000. Anyways, oh sorry, that's another story for another time. I just told it to you. Wait, it's the story for this time. Okay, so we'll multiply this by 1,000, or since we have a positive exponent, we'll make this number bigger, and the way we make it bigger is by moving our decimal place to the right. So 6.022 times 10 to the third power would be 6,022. That's a big number, right? Of course, depending on what it is. If you've got 6,022 pennies, it's only $60. Which that's kind of disappointing. You're like, man, I have 6,000 of these coins, taking up a whole bunch of space. It's only $60. But what are you going to do? I mean, you could pull the penny out of circulation, but nobody wants that. Okay? But this is already a big number. 6.022 times 10 to the 23rd power. That is a huge number. That is a huge number. And I know what you're wondering. What on earth does this number come from? Because I can't even imagine having that amount of something. Like imagine what 6.022 times 10 to the 23rd people would look like. I mean, that's outrageous. It's a lot of people. That is a lot of people. Or even something smaller, like 6.02 times 10 to the 23rd fruit flies. Right? Fruit flies are tiny. But man, imagine what that would look. I mean, it's a number that's so big, it's hard to even imagine something that big. At least for me, but maybe you're better at imagining things than I am. But the reason why this number is significant and where it came from is it allows us to measure the amount of something as small as an atom or something as small as a single molecule of something, and to actually measure it in grams. I don't know if you knew this or not, but an atom is really small. Really small. And I don't know if you knew this or not, but a molecule, a single molecule of something is really small. Now, some molecules are bigger than others. Not all molecules are created equally. But in order to get enough of these that we can actually measure it in grams, we have to gather these in moles. So how many of you remember when we were taking our mass of that rock in grams during our first class time, how many grams are in a pound? Anyone remember that? It's about 454. So there are 454 grams in a pound. So a gram is not that much material, right? And then to think that there are 6.022 times 10 to the 23rd of something inside of something that small, it's impressive, right? These are tiny, teeny, tiny little things. So specifically, we got this number from carbon, although you can apply it to any element on the periodic table, which you have a periodic table in your book. 1 mole of carbon has an atomic mass of 12.01 grams. So if you take 6.02 times 10 to the 23rd carbon atoms, you get 12.01 grams worth of carbon. And remember, there are 454 grams in a pound. So true or false, this is a lot less than a pound. True. So that's a lot less than a pound of carbon, and there are 6.022 times 10 to the 23rd atoms of carbon in it. This gives you an idea that there's a lot of matter in this universe, right? We're talking about a lot of matter. A lot of matter. Well, what about a molecule? Let's say something like water. So again, we'll talk more about this in the coming weeks, but as we look at water, can everybody see water written here? Can you see it, Stephen? So H2O, it's got both hydrogen and oxygen. It's a molecule, it's not a single atom. And so if we have a mole, we got together a mole of water, it would have a mass of 18.01 grams. Still, much less than a pound of water, which a gallon of water weighs about 9 pounds. But just in a single mole of water, we have 6.022 times 10 to the 23rd molecules of water. It's a lot of water. So then how many molecules of water are there in a gallon of water? A lot. But now you're equipped to answer that kind of a question. take you a couple of steps to get there, but you could answer a question like that. Okay? Any questions on this? I want to show you one more measurement, and it's called molarity. Molarity is equal to the number of moles of solute. We've seen this term before on our previous slide. Don't worry, I didn't have you look it up on the previous slide. We'll look it up this time. I know you worry about those kinds of things. So molarity is equal to the moles of solute measured in grams. Oh gosh, not measured in grams. That is a typo. I need to fix that. Because we don't measure moles as a number. It's not measured in grams. Do not write that. No, I'll fix it right now. I don't know how that happened. That's terrible. Sorry everybody watching this recording, which may include some people in this class. That's embarrassing. You all deserve better than that. Okay. The moles of solute in moles divided by the volume of the solution in liters. Okay, and that's molarity. The moles of solute in moles divided by the volume of solution in liters. Making good time. All right. So here we were making solutions based on percentage of total mass. Now we can make solutions based on molarity, the number of moles of a material dissolved in water. You're excited for this, right? You're like, it's Monday. I don't get excited about anything on Mondays. Except a nap, food, or going to bed for the day, right? I get it. Okay, so what are some important measurements? Answer this question with C-list. S-E-E space L-I-S-T. I don't want you to write C like the letter C. Just answer this question of C-list, and then that'll force you to go back here. Because really, I can't just go through and, pick one of these things to answer it. So just write C-list. And then two key terms. One, solute. Solute. S-O-L-U-T-E. Solute. And then the other one, a mole. But make sure when you look up a mole that you put in chemistry. Because otherwise it's going to give you more definitions than just how it's applied in chemistry. A naked mole rat is not a mole at all, nor is it a rat. Anyways, it is a rodent though. Do you know the naked mole rat? Y'all know? Okay. Okay, any questions about this question? We need to start working some problems. So how can we use this idea of molarity, or the moles, to make a solution? I'm glad you asked. So here's us making this salt and water solution, right? The one we already talked about with our 35% water solution, or salt solution. So first, we measure the mass of the solute in grams. That's step one. Measure the mass of the solute in grams. Measure the mass of the solute in grams. That's step one. Okay? Step one, accomplished, right? We already did that. Although that rock's not going to dissolve in water. At least not right away. It'd take time. And then it's not really dissolving in water. It's being broken down. Anyways, it's going to take some time. Then we divide this number, the one we just got by measuring the mass of our solute, by the atomic or molecular mass in grams. So this would allow us to figure out not just how many grams of salt do we have, but how many moles of salt do we have. How many moles of salt do we have? So we divided it, we got grams. Sorry, we measured it, we got grams. We divided that measurement by the atomic or the molecular mass. In the case of salt, it's going to be the molecular mass. After dissolving this salt in the water, we'll measure the volume of that solution. Okay? Why would we do this after dissolving the salt in the water? True or false? Salt takes up space. True. So true or false? Putting salt in water will increase the volume of that solution. True, right? We want to know the total volume of this solution. So we measure the volume after we dissolve the salt in the water. You know, like if you're just putting a little bit of salt in, it's not going to make a big difference. But if you're making a 35% salt solution, it's going to make a big difference. It's going to make a big difference. Have any of you ever collected ocean water and taken it home? Do it the next time you go to the beach and then just leave a cup of it out and the water will all evaporate and it'll leave just the salt that was in the water. And you can actually see how much salt was in that amount of water you took from the beach. Don't do it from a protected area because you'll get arrested or fined. But if you do it from a public beach, nobody will care. So I want you to go do it in a marine protected area, and when you get arrested, tell them I told you to do it. I did not tell you to take water from a marine protected area. It's on the recording. It's evidence. Okay, so then to calculate the molarity, we divide this number, right? We got this number in moles. By this number, the volume of the solution in liters. We saw on the previous slide, moles of solute divided by liters of solution equal molarity. Okay? I know what you're thinking. Like, Dr. Engel, this sounds wonderful. Sounds like this would just keep me busy for days on end. But I want to actually see it happen. Let's do some problems. That's what we're going to do. I'll give you everything you desire. As long as your desires align with my desires. It's like, how do you get everything you want in life? You want what God wants. You'll get everything your heart desires. It's another story for another time. All right. So how can we use this to make solutions? For this one, write C directions. S-E-E space D-I-R-E-C-T-I-O-N-S. Wouldn't that be funny if I misspelled it? Yeah. I don't think I did, though. Okay, because I mean, these are the directions of how to do it. We can't like take one piece of it and pull that out. So this is a framing question. We have to see the directions. Okay, you ready to do it? Let's do some problems. Yes, yes, yes. So what is the molarity of salt solution if 3.55 grams of sodium chloride of salt are dissolved in 5 liters of solution? Okay, so here's another framing question for your notes. Underneath this, you'll put the work and then put your answer over in that smaller column, right? We get into the habit of we write the answers to our questions in that smaller column. Well, the answer to this question is going to be a number, right? You put a little box around it or put it inside of a heart to illustrate the passion that you feel. Okay? What is the molarity of a salt solution if 3.55 grams of sodium chloride are dissolved in 5.00 liters of solution? Okay. So some things that we have from this problem. By the way, I will go in afterwards, before I send you these slides, I'll go in and put all of this, what I'm writing on the board, onto this slide, and then send it with you. Okay? So here we're given, we have 3.55 grams of salt, and we are also told that we have 5.00 liters of solution. Now, does it tell us what the salt is dissolved in? Nope, so what do we assume? It's water. Why?
Universe.
Because that's the universal solvent. Okay? So what do we have? We have these two measurements. What are some tools we have to use? What are some tools we have to use? Do we have any tool that we've seen so far today that includes these values? We have one that says molarity is equal to moles divided by liter, right? Right there, we're almost there. We don't know how many moles of sodium chloride we have. We do, however, know how many grams of sodium chloride we have. Not much. How you doing, Nathan?
Good.
I want to find the periodic table in this book so that you have it at all times. Oh boy. On your back cover, just before the back cover, there is a page, and it opens up, and that is a periodic table. Man, that is in vibrant color. Gosh, that almost pains my eyes to look at it. The nice thing about this is you can look at any element on the periodic table and it will tell you its mass in grams. That number in the bottom right-hand section. Again, we'll talk about all this in the future, but you see the big picture of uranium in your periodic table, and then on the bottom right, it's pointing to it and it's saying atomic mass. That's the mass in grams of a mole of that atom, right? We've been talking about that today. So we could do this for sodium, and we could do this for chlorine. And we know that sodium, according to this, has a mass, oh man, let's just call this 23 grams. 22.98976. I'm almost offended that number is so precise. We'll call that 23 grams. What about chlorine? Y'all looking at your periodic table? What's chlorine?
35.4.
35, and let's call it 35.5, because 4 will round up. Let's call it 35.5 grams. Okay? So if we have a mass of sodium chloride, a mass of salt, a mass, yeah, I mean, if we have a mass, that's fine. But if we have a mole of salt, we're going to have a mole of this and a mole of this, right? We've got a mole of it, we have a mole of salt, and we have a mole of, a mole of sodium and a mole of chlorine, right? We okay so far? So, sodium and chlorine together then is going to equal what? How are we going to find that? If my mass, let me see, what is it in kilograms? 151 kilograms? That's not that much. 146 kilograms, and the mass of all of my children put together is like 47 kilograms. What would be the mass of my children and me together? How would we do it? We add them together, right? Look at that. Critical thinking. 58.5 grams. So that's how much a mole of sodium chloride masses. 58.5 grams. 58.5 grams. Okay? Well, it's cool. Like, we've got some tools now, but what do we do with them? Have we solved the problem? Nope, we sure have not solved the problem. We've written down what we have, what this problem gives us. We've written down some tools that we can use. The last thing we need to come up with is, what does this problem actually want from us? What does the problem actually want from us? What is the molarity? So it wants molarity. We have our tool for calculating molarity. What is it? Molarity equals moles of solute divided by what?
Solution in liters.
Volume of solution in liters. Do we know the volume of the solution? We do, right? That was one of the things the problem gave us. Do we know the moles of solute? Not yet. Not yet. Okay, so we need to figure this out. Moles of solute. So here's another tool for you. Moles of anything is equal to the total mass divided by I don't want this box to be in the way. Total mass divided by the atomic or molecular mass. Okay, atomic if it's a single atom, molecular mass if it's an entire molecule. Okay, do we know this? Look to see what the problem gave us. Do we know the total mass of the salt that we have? We do, right? It's 3.55 grams. Do we agree? Disagree? We agree. Okay, I see some like yes with a question mark written after it. Like yes, but I'm not really convinced that it's yes. Maybe? Okay, our total mass of salt is 3.55 grams. We divide that by our molecular mass. What is our molecular mass of salt? We got that from our periodic table and doing some addition.
58.5.
58.5 grams. Okay. 3.55 divided by 58.5. 0.06 grams. Oh my goodness. Grams cancel. We're left just with a number. And what is this number? It's the number of moles that we have. Right? Okay? So we have much less than a mole of salt. That's okay. We know a mole is a huge number. So even just having a fraction of a mole is still, it's a lot of salt. Are we done? No. All we did was get this. But we haven't found molarity yet. Now can we find molarity? Yes, we can. It's a lot of fun to solve these problems, right? Not all of them are this complicated. By the way, you're not going to be fully equipped to do all of the chapter 4 worksheet yet, because we have to do another type of problem. So if you get to there, don't try. I mean, you can try to figure it out yourself if you want to, but we'll actually begin our time next week finishing chapter 4 and then going into chapter 5. Okay? So now we can calculate molarity. Molarity is equal to what? What goes on top of the fraction? Moles of the solute. And we figured that out. How many moles of solute do we have?
0.06.
Good. Thank you, Charles. 0.06 moles of salt. Do we know the volume of our solution? We sure do. It was given to us in the problem. 5.00 liters of solution. And why can't we just call it liters of salt? What's the salt dissolved in? Water. Why can't we just say liters of water? Because it has salt in it, right? So we'll call it the solution. We've made a simple solution, something dissolved in water. And now we'll calculate this, and we'll do 0.06 divided by 5.00, and we get 0.012 molar. You're like, wow, this was awesome. This was everything I've been missing from my week is now present. I'm complete. That was a complete square. You see, nothing missing. It's whole. I could have done a circle, right? What do we think? Is it doable? Get some practice with this over the next week. You'll get some practice as you read through chapters 3 and 4, as you work through some of these problems. And then when we come back a week from today, we'll do some more of these problems. We'll actually work them backwards, where we're given the molarity, and we have to figure out how much of the solute we have. And then we'll move on to the next topic. Okay? All right, and then you'll get more practice too, because I'll send you home with a quiz next week, and it'll have more problems like this. So you get lots and lots and lots of practice. And by the way, the quizzes, I'll tell you this now, it'll be on the recording so you could hear it, and there's evidence for it to support if you're like, hey, you forgot to do this, Dr. Engel. The quizzes will always be graded based on completeness. If you answer all the problems, you will get full credit on the quiz. Exam doesn't work that way. Okay? Exam doesn't work that way. Exam, your answers have to be right. Okay? Cool? Any questions, thoughts, concerns? Okay. All right.